Thank you very much for the introduction, Enrique. Yes, I studied here. It's great to be back, to have a reason to come back to Erlangen. I finished my PhD in 2007, so it's been a while. But this room did not exist back then. I want to talk about what I summarized here in the title as AI components in PDE solvers. And then I noticed, oh, right. The spoilers already, yes, exactly. It's actually potentially a good keyword that summarizes the topic are those differentiable solvers in the subscript here. Those are actually playing the key role, but I'll explain in a moment how those two play together. Yeah, let me start very broadly. So we're dealing with PDEs, with physical systems. PDEs basically give us a language to work with and model and ideally also understand what happens in nature around us. So in my group, we are often working with fluids. As you can already see here, the air in this room, right? You don't see it, but it actually has a very complicated motion. It's more obvious if you look at liquids. It's actually two-phase flow, right? You have water and air. We usually see it from the air, so we look at the water. But Navier-Stokes underneath is a very similar and unifying description of it, or it's also an important topic. It keeps the airplane upright. Lift and drag are very classic themes for transportation and play a role in many real-world applications. Now we have these AI technologies, and it used to be necessary to motivate why this is worth looking at all, and whether in the context of if we have a physical model, whether it makes sense, and so on. By now, I think Thürey and Nobel Prizes indicate there is something that's worth looking at least. So there are definitely many open questions, but it's pretty established by now that it's a pretty powerful technology that is worth considering. And the general kind of theme and goal with this combination is, of course, we have these PDEs, we have a lot of classic tools to solve them. How can we now leverage these new techniques that have come up from the field of AI to improve of what we can do with PDEs and our capabilities of solving them? I also do want to distinguish two kind of main trends as I see it in the field at the moment. So the arguably more shiny one and more prominent one are these foundation models, right? There's a lot of topics in the news dealing with that. That's what drives ChatGPT and co. There's the second one, which I think is at least as important, and time will tell which one is the more important one, but that's what I want to summarize here with these differentiable solvers, and that's what I want to focus on today as well. And we have a highlight here, right? So I will basically not talk about these foundation model topics in the following, although there are interesting connections between the two, but I'll focus on the solvers. And no matter which subfield you take, generative modeling with AI is also an interesting one. I think for all of these, it is actually now a good point in time, I think, to look at it, because they've been in the works for quite a while. It's still a quickly changing field, but it's about time that they actually have real-world impact. And I think by now with the technology, we're actually close to making those steps. I think there is a lot of potential. Within this kind of distinction, the previous slide hinted at that already, but there is one fundamental conceptual difference between these two approaches that I think is worth highlighting here again with this picture more clearly is, if you look at this foundation model or surrogate training approach on the left here, then basically we are giving all the work to the neural network. And neural networks are behind all of this. I hope that's clear. So basically, if we're looking at large trained models, the network will replace everything and be the only thing that's left dealing with providing solutions to the PDEs, whereas in this context of differential solvers that I want to focus on the right, we'd actually keep the solver around. So we are not, the goal is not to completely replace the PDE solver in the classic methods, but to kind of let the neural network and the solver work together. So in a way that gives hybrid methods, and the field partially probably owed to its dynamic nature, but is not very good at unifying terms. So there are all kinds of names that you find for these combinations in the literature, right, from hybrid to super solvers and all kinds of variants. So I will focus on the right side, and the names that I find most intuitive in a way and will try to stick to is that on the left side you have a pure prediction task, meaning the network, right, has a sole job of predicting the next step. And on the right, in contrast, we still have the solver. So the solver outputs something, and the goal of the network is to correct that. So I'll talk about those two different scenarios and learning tasks as prediction tasks and correction tasks. And I also do want to point out, we're dealing with physics, of course, and physics-related losses, but I will not be talking about pins. So just to, it's a common question, so I thought it's worth having that on the slide. None of the topics I'd be happy to discuss in more detail why and where the differences are, but what I will talk about is actually not dealing with pins. The connection to dynamic systems is, I think, a bit more obvious. So in a way, we have a PDE, right? You can imagine being of the form shown here at the top. So we have time derivative, depending on some other derivatives, spatial ones, all kinds of orders on a certain computational domain. And then, right, we have a solution operator that maps some initial condition, U0, to some later evolution of a system in terms of U at a time we're interested in. So mapping from the some given state, maybe some synthetic initial conditions to some developed turbulent equilibrium state or so. And now, in this context, we like to, for example, train a network that takes one of these states, not necessarily the U0, but some state at time t, and maps, given parameter theta, the state to some time increment, normalized to 1, so some next time step. And right, you can see that as a basically neural operator, or right, basically it's not too far then from a numerical stencil. It takes one part of your solution at time t and basically integrates it in time to the next point in time that we're interested in. And just to highlight it, so right, this is actually now also close to what numerical solvers classically would do. Right, we have a computational domain. In this case, we assume everything is discretized both in space and time, and then we have we can pick any of these points. Right, our operator should work on all of them, but if we pick one of them, we have a solution at time t that goes into the network, and then the network produces at that point, typically looking at a more or less local neighborhood or receptive field, the solution at the next time step, and this will repeat for all the points we're interested in. Right? And then we have the whole computational domain as shown here at the state of the next time step. Yeah, and now our network should actually replace the solver here in the simplest case and provide that solution for you on this domain that we chose. I want to now simplify this picture a bit. If we talk about this network, and we can still keep in mind that we go from an earlier to a later time step or initial condition to some time averaged solution, but you can think of it as basically getting an x and producing a y. To just make it a bit more easy to read here, as shown at the top, and I'll typically denote the ground truth values with a star superscript. So this was a network version, so the f theta is some neural network. The architecture won't matter a lot. I will actually not talk about details of architectures. I assume you can choose a suitable one for whatever domain you're working on. Then this would be actually with the naming scheme from before, a prediction task, right? Here the network produces the output, and we might have a solver. So if we take the PDE, we discretize it, then we have a numerical solver, and we can give the same task to the numerical solver, and might also be able to approximate a ground truth solution here, experiment in this case or so, in the same case. So I will denote the solver, which I will keep around. Right? We're not trying to fully replace it with the P here. All right, this could now be Navier-Stokes. We might have a discrete version of Navier-Stokes that does a time integration for some chosen interval. And the kind of main ingredient that I've I've already mentioned before is that now we want the solver, this P, to be differentiable. Meaning, and that's now why it's useful to shorten it, we actually want a derivative of what the solver produces, the output with respect to the input, the x. It's really just a derivative, a linear approximation of the whole change. In a way, not too complicated, but that is what actually drives all the learning processes, right? They work with gradients. It's a first-order optimization, and it's not taken for granted for solvers to produce these or to be working with this for optimization tasks. So this is actually a central quantity that will come into play for pretty much all of the following examples. Right. Should point out, of course, this is, if you write it out like this, these partial derivatives are a whole matrix. It's a Jacobian. Right? It's in the simplest case, if the example from before, if we're working with states, it's a square matrix, output to input states, however many spatial samples you chose. And what turns out to be useful in the context of gradient-based optimization and learning is that typically we have a scalar loss at the end. So we have some energy function or some scalar quantity that tells us what's good or bad. You can imagine it as a kind of height field, and that being scalar, right, if we multiply it with that Jacobian matrix, it turns it into a vector again. And in this case, actually, it would just have the same dimensionality as the x itself. So we have an update that has the size of these individual states that depends on some loss formulation. Could be L2 or a distance towards some ground truths we might have, or could also choose others here, but the simplest case, actually L2 is often a very good starting point. And it's a classic gradient. So if you imagine the energy landscape also shown here in the picture on the left, right, the gradient is perpendicular to these iso levels of the loss, just points down. It's a very classic and known quantity in a way. And this is what we typically use for the learning itself. And where I'll now try to motivate the following, that this is also really useful to have for solvers themselves. Yes, a bit about the notation. So the naming scheme, it's not, the terminology is not too centralized. I think a good name for it are actually differentiable solvers. Or you could also call it differentiable physics to differentiate it from differentiable other components that you might have, differentiable rendering techniques or so in the field. There's a whole, within deep learning, a whole field of differentiable programming, right? You could make any processor, any calculation differentiable, but I think for the context of this talk, actually the physics solvers are the most interesting component. And in the end, it's actually not too different from running adjoint methods or reverse mode, autodiff, or backpropagation is essentially using just that. So it's important to point out that in a way, these are all pretty much equivalent and summarized under these keywords in the following. I think a good way to motivate this combination of having a solver, a differentiable solver, and neural networks is in terms of this book, Thinking Fast and Slow by Daniel Kahneman. Has anyone read this? It's a very nice book. I can recommend it. It has nothing to do with neural networks. It talks about how our minds work. And he explains, or basically builds an intuition that our brains work in terms of two different systems. System 2, an analytic, slow process that happens when you take a piece of paper and start writing down things. And a fast, intuitive process, what you're doing now, looking at the screen and listening to what I'm saying. That is the system 1, he calls it. And he argues that they really work very differently in our brains. And in a way, the picture, I think, does transfer over to the scenario here with the differentiable solvers. The solver is still basically a classic numerical solver that you can see as a system 2 basis, an analytic stepping process. And the network, in contrast, provides a more intuitive, fast correction on top of that. And I think this combination does actually make sense, and it's also nice to see this over time, right? So you could have many steps of this numerical solver working together with the steps of the neural network. So also in the following, I'll have quite a few examples from time-stepping systems, and then we actually iterate on each of the updates provided by the solver and by the neural network themselves. For adjoint methods, I should point out that there are some differences in how you apply it. Classically, for joint methods, you can actually give or get substantially different formulations if you really formulate your whole optimization problem beforehand and then discretize it. That is kind of the classic joint method approach. It's a bit less flexible. So I think that's partially why it's only used for specialized applications, because whenever you change your formulation or what you're working on, you basically need to change your continuous formulation first and then rediscretize, which can be tricky. It's often not non-trivial to turn a changed formulation into a solver again. And I think this is, in a way, one of the key conceptual advantages of the other approach, to first discretize and then optimize, because basically, you can work in pieces. If you have a discrete operator for some part of your system, then you can combine it with others. You can keep it around, basically. You can still solve optimization problems with that very conveniently. And still, you really get accurate gradients for each of the pieces, and you can put them together with a chain rule, so it's accurate, but it relies on an existing discretization beforehand. So I won't write it out, but with a chain rule, then you can combine these very flexibly. That's what happens if you've used any deep learning framework all the time. Any activation function or any content that you call basically run this process, and it works just the same way with the numerical solver. So that's also what we often do. You can basically see a Navier-Stokes solve or any physical PDE solver as another layer in your networks, just changing the state. If they provide a gradient in line with these neural network components, then you can work with them just like with any other part of the learning pipeline. Yeah, and for example, if you can propagate the gradients, you can then also typically very easily divert the gradient at the update to some different quantity. Say, if instead of the state, you want to optimize for some material parameter. That is often quite easy to do. All right, so much for the setup. I do want to come to some examples of how that works in action. Before I do that, okay, let me talk about a few more of the subtleties that arise. So now I want to come to the process over time. If we're dealing with these pure predictions, just to contrast it, if we have a Markov process, so just depending on the current state, and we use a network, then we can basically produce a chain over time by evaluating our network. So we can take some UT, cursor, some state, evaluate our network, to basically produce states in the future. Assuming we have ground truth data, we can compute a loss, and then train our network through these chains of evaluation to produce better states over time. It's actually quite easily implemented and also very easily written out. What is important to point out here already is if we do more than one step, if one step, I evaluate my network, a new step, I compute a loss, then I would just go through the loss back into the network. That is quite obvious. As soon as I do a second step, I already have multiple gradient contributions to the network, right? Because from the second step, now I have another loss evaluation that goes into the second network call, but this goes back into the first one because the first evaluation of the network contributed, right? So I have in total, basically now from this one additional step already 3 updates of the network parameters theta. I have 3 gradient contributions, and it basically grows quadratically with the number of steps. But this is now only the network unrolled over time already. Now, one difficulty that arises from this is that the network now produces these states, right? The U here are produced by the network, and hence they don't exist before I'm training, and they probably don't perfectly align with my ground truth data. So in terms of the distribution for learning, those U actually now look different from what I pre-computed, different from my targets, and they change over time of the training. So this is actually, right, in a way, a changing target, and is a classic data drift problem, if you want. I have data that changes here that I need to produce by evaluating the network, and nonetheless, I want these changing distributions over time to match the data that I have in terms of the ground truth. So I've just shown two of these steps, of course, but normally, right, especially if you think about something like Navier-Stokes, these simulations should run for thousands of steps, right? Navier-Stokes, if working well, it's a chaotic system, right? It's turbulent. It might have very complex evolutions over time, and I want the network to capture these. So what's in practice very likely to appear is that you can analyze this in terms of the Jacobians of the system, that we have parts that actually exponentially grow, system basically modes in your states. Those then would show up as exponential accumulations of these errors and explode, or parts that get dissipated, they basically would converge and give you something constant. And both are basically not what you want from a chaotic system, right? It should basically continue fluctuating. It should show the distribution of the straits that, right, your turbulence or so should exhibit. So both of these actually mean that the network does not have the correct butterfly effect, but produces, right, something completely unphysical. And that is a challenge. Here's a nice illustration from Sora, I think, in this case. So we basically have training data that we're dealing with, but the network produces different data, as what's supposed to be highlighted here with these different colors in the different data sets. So it's, right, the data that the network produces is different from anything we can produce or pre-compute. And right, in machine learning, this is a data shift problem. The previous case was this pure prediction scenario where we only have the network to produce the states. The same actually happens if we go to these correction tasks. Right? So in the previous case, we didn't have any solver. That's basically not the case I want to talk about, but it still happens if we have a solver. So it's just slightly different in terms of setup. Now we have, or we need some target. It could be an experiment, but we can assume that we have some ground truth solver, the P star here, that produces the ground truth states. And we have another solver, a low fidelity solver, right, maybe coarser spatial and temporal resolution, that produces that is integrated into the training. So this, right, should be fast. We really need to run this at training time. And the chain of unrolling then looks like this. We're basically just plugging the solver into each of those steps to produce the outputs, and one state goes into the solver, then it's corrected by the network to produce the next state, ut+1. And this continues for, right, any number of steps, basically, but the challenges of unrolling and the data shift remain the same. I hope that's clear from the picture. It just additionally goes through the solver. So the nice thing is basically intuitively, also in this chain, if you look at it, the loss from here propagates through the network, through the solver, and the first network, in this case now especially, gets feedback from the solver, intuitively feedback about how the physics updates as prescribed by the numerical solver should be reflected in the state of our neural network parameters. Yeah, so that's what you can also see as a solver in the loop training, right? We're unrolling these steps now, and the solver, the physics solver, P, now stays in this unrolling chain and is part of the process, meaning it actually needs to be run both at training time as well as inference time. So I do need to keep around this P for later on using the model. The model by itself would not produce meaningful states. I hope that's clear. Right? And we've tried this by now in a variety of settings. So here is one scenario from a turbulent mixing layer case, where you basically have two different fluids with different speeds that lead to shearing and then vortex formation in at the interface between these two parts. And here you can see already the output of the learned solver. The ground truth looks very similar. I hope you believe me here. And at the bottom, you can see the corrections that the neural network node does. And just intuitively already, it's good to see that they're localized around around the vortex shedding in the center. And I'll come to some more evaluation of this case in a moment, but just to give you some intuition for how this could work. And also worth pointing out, the solution at the top actually now does run both the low fidelity solver and the network, and the solver by itself would actually not produce any of these vortices. Yeah, so this is already now showing actually one of these component-wise combinations in action, and it's worth mentioning now, so this is where the title came from, basically, right? We have this core solver now that does something in the right direction, but does not get the answer right, and this is now kind of augmented by a learned component, by this AI component, and then, right, those two run over time to produce the solution. Now, in this case, also for several hundred steps, or even thousands over time. Right, so this was just qualitative. This is a very classic case, so we can actually really measure how well this worked. One of the classic quantities to look at here for Navier-Stokes is the energy spectrum, of course. For this plot, you can see the ground truth in terms of the orange dots. This is from a DNS, so basically fully resolved simulation, and then different neural network combinations in green, and the pure solver case denoted as no model here in blue. And the spectrum is actually fairly forgiving for fluids. We noticed in several settings because it aggregates so much, but you can already see the no model case, only the lower solver basically is strongly underrepresenting most of the frequencies, whereas the different neural networks seem to overall be much closer to the ground truth here and don't differ too much. So these three networks now differ in terms of how much of this data shift they were exposed to in the number of steps that were enrolled. So this is 10, 30, and 60 steps. And here the differences are not too big, but if we look at different quantities, for example, the Reynolds stresses, the amount of mixing happening in the flow, then things start to separate here, and it becomes apparent that the model chain, the longest in this case for the 60 steps, actually now starts to really get this behavior right. These Reynolds stresses were not as part of any loss. This is, in a way, a nice new view on the data that's produced. But if you unroll enough of these steps, then the network also manages to correct the core solver to get this mixing behavior right, as shown here in the plot on the right. And now, of course, this still uses a solver, so it's purely synthetic. In this case, a good question is, well, what do we gain from this combination? And because we have control of the solver here, we can actually now do a fair comparison. I would argue, generally, as a word of caution, I think also, especially in some older papers, you can see comparisons between something trained and then the data generating solver. So in this case, that would be the DNS solver, but that's much more accurate. So in a way, that's not a fair comparison. But here, having control of the solver, we can run the same solver on the same hardware on the GPU and lower the accuracy to match the accuracy of the neural network here, of, say, the green line, and then comparing on that level of accuracy. And in this case, also the same hardware and implementation, and we still see more than an order of magnitude speed up. So this is a nice indicator. It's definitely a contained case, but right here, this pre-training in a way does pay off. And also, it's a classic trade-off in a way. The network is more specialized. It's definitely not as general as the solver itself. But for this kind of set of solutions and problems, it does give a speed up. So if you know you need to solve this case many times, then this might actually be worth doing at pre-training. Yeah, so I've mentioned these prediction and correction tasks, and we've tried this in a variety of settings, also with different networks and so on. And at some point, we had enough of these trained networks, several hundreds, that we thought it's actually worth looking at how the differences turn out and having control of it. Especially if you have the setup with the solver, it's very easy to turn this into what I called earlier the prediction scenario where we basically take the solver out. So we can compare if we give the task to solve this PDE over time just to the network. You can train this, you get certain solutions. That's actually shown here as in terms of the orange bars. And it's already obvious, I think the orange, these are all relative errors. The orange bars are all higher. If you do the same tasks with a solver that does something useful, as in these cases, so by itself, the core solver, this approximate one, is typically not stable and so on, but it does a step in the right direction. And then on average, we notice that across all of these cases that we ran, you get at least an order of magnitude more accuracy in terms of relative errors. So it does pay off. It's actually not too surprising in a way, right? The correction task is easier. We have a solver. It does require some additional time also. And this initial prediction, right, the network can build on. So it does have more help in a way, right? For the prediction task, the network needs to do everything from scratch. It's a tougher task. But still, it's nice to see there is an advantage if you have a solver that goes in the right direction. This seems to be a good idea. Now, also for us, one question or talking to people is, right, it seems to work well, it's nice. Also, it generalizes actually nicely in terms of parameters, also in time. But why don't people use this more? Well, right, it's actually not so easy to pull off, right? It might be a non-trivial task for many people if you're not developing solvers to put a solver into the training loop. So that is worth mentioning. It's definitely, or unfortunately, it's not a given that solvers provide these gradients, that provide the integration, and it does require additional training costs because we do need to run the solver, this approximate solver, both at training time and later on at inference. That's potentially less crucial, but at training time, there is a higher upfront cost for training these models. The field has improved a lot, I think. So we've, over time, worked on all kinds of variants of solvers and colleagues, for example, TUM, working on these JAX fluids frameworks, or also by now in weather prediction. This has been quite active. There are various efforts to produce differentiable solvers for weather. So it's nice to see that there is a lot of catching up in different fields. So I think especially the latter point, like where to get a differential solver from, this is improving, and I think we have more and more to build on in the future. Now, I do want to show one other recent example from our group, from the PICT solver, as we called it. This is now a 3D Navier-Stokes solver, also going towards these real-world applications. So far, I've shown 2D examples. Our world is in 3D, and many flow problems are. So here's an example now from a 3D case. An interesting problem that arises here, also with these time evolutions that I've mentioned before, is that for chaotic systems, having a direct state supervision, right, a direct target with an L2 loss might seem dubious, especially if you think about chaos and matching statistics. To compute a direct L2 difference or any direct loss term is potentially not helpful or worst case wrong. So what turns out, however, to work nicely and is an interesting variant is to directly supervise in terms of statistics. So if you know how your turbulence should evolve, what kind of distribution it should show, you can actually train with this distribution directly as a loss term. And we tried this for Navier-Stokes here for a turbulent channel flow. So now you can see it in motion. So this is a cut along the walls. Basically, there are two plates here at the top and the bottom. The flow evolves in the center. So it's also a pretty classic case. Very simple geometry in terms of the walls, but nonetheless, it's a turbulent one. It's really a 3D case with 3D turbulence. So we have vortex shedding and turbulence formation in the bulk in the middle of this flow. And because it's well studied, we also have reliable statistics to train with in this case, from a spectral solver, shown here. And another point that comes into play here that turned out to be really useful is not only to expose the training to multiple steps of the system, basically to train with, but to basically push this further by just computing additional steps without a gradient. So this is another variant that I do want to mention here. I had a picture like this on the slides before. What you can basically do is you can do multiple steps here, shown on the left, without backpropagating. So actually, this loss should also be gone, I apologize. So here there's no loss. The loss is only computed here for later steps. So we're basically just running our solver and the network multiple times to produce these steps without backpropagating or updating the weights. And then we run several steps, again, with the solver and of course the network, where we now compute a loss and really change the parameters. And these are basically, you can see as warm-up steps. So for this case, we used almost 100 of these warm-up steps to expose this distribution. And then, actually, we could also vary the second one, this actual unrolling with gradients, but we just kept it fixed at 12. And for this really more turbulent 3D case, this also turned out to be an important component to really expose the shift in the data and let the network train with, basically see what kind of states arise from the learned combination. But together now with the solver and the network, it's a relatively simple CNN in this case. We can now train for these 3D turbulence cases. Here you can see some still images of that. So purely the low fidelity solver, the P from before, the reference, or if you compare these two, obviously has different frequencies and different contributions in terms of these. In this case, it's the tangential velocity. Also, for comparison, normal subgrid models do not compensate for this, and the learned variant does actually, it cannot resolve. It has actually the same resolution as this one, but resolves the frequency of these vortex shedding channels basically much more accurately. And over time, it also behaves quite nicely. There are different variants here, but the losses now, with respect to the spectrum of the basic versions, are here at the top, and different learned versions at the bottom here. So it's actually more than an order of magnitude speed up for these. Especially the orange one, the purple one here is the kind of main variant. The other ones are different optimizations in terms of the backpropagation for the solver that you can do with effects, but I don't want to go into the details. And again, because this is now all running on the same hardware, we can measure how much of a speed up we get. In this case, we did use OpenFOAM as a baseline. If you also compute the whole solutions with the same solver, it's actually not much faster than OpenFOAM, because OpenFOAM has some really nice preconditioners for these cases. But even if you use these preconditioners, there is a nice speed up. In this case, I think it was around 40. And also the number here. So for each of these steps now, roughly 40% are taken by the neural network and 60% by the rough solve. Just to show as an example, so this potentially does extend to turbulent systems and to 3D systems as an outlook. Another interesting outlook that I did want to mention here are generative models. So far, all of these neural networks were kind of classic neural networks that just produce one output, deterministic, one-step prediction to give the next state or the correction of one of the states. However, these diffusion models are really an interesting and also quite promising trend within the machine learning field. Here's a very rough rundown of the main approach. So we're trying to learn some signal, shown here on the left. This again, just to pick something, a steady state flow around some airfoil. We basically first destroy it in terms of pure noise from a known distribution. And then we try to map from this known distribution, which we can relatively easily sample from, back to the complex distribution of the data. And the nice thing now about this is that potentially we are allowed and we can learn to reproduce multiple answers on the right-hand side. So before we assumed that we have a single answer, and now the solutions could actually have different modes of behavior or so. And even in this generative setting, I want to now motivate that incorporating solvers into the training and inference is actually promising. So likewise, here the motivation to do this is to use the solver to produce more physically accurate outcomes on the right-hand side. And we're trying to learn this reverse process from noise back to the data samples, right? So the solver would also come back into play here, both potentially at inference at a training time, and importantly, if we have a differentiable solver for training, we can again go through the solver back into the weights of the network. So the differentiability, even in this process, is actually still important, because for training, what we want to have is a change in the parameters theta of our neural network. So having a differentiable solver is also really paying off in this case. The two options that I mentioned before do make quite a difference. For these diffusion models, an important point is they are iterative. They don't produce the answer in one step, but they work with the noise. But classic diffusion models need 1,000 steps. Even modern variants often need 10, or depending on how well you can compress them, basically into fewer steps, at least a handful, so they are more expensive. So if you use something like a physical model at inference time now, you actually typically need to use it at every step along the way. So if you do standard diffusion model, you might need to run your physical model many steps, which is a special implication of these generative models. At training time, in contrast, you still have the same trade-off as before. The training becomes more expensive. You do need to evaluate your physical model at training time. But ideally, if you do it this way, then later on at inference time, the model is not slowed down. But you can basically, ideally, get your model into a better or into a state that produces more physical answers. But then at inference time, you can potentially leave the physical model out. Yeah, and this is one variant that we tried. So this is an overview of different methods that do these different combinations. And first of all, what we notice is that there is an important trade-off between basically the physical accuracy and the distributional accuracy. For generative models, it is actually one of the key goals to have these different answers. If you overdo it on the physics side, intuitively, you converge to a mean, you get a really good match of your physics residual, but you might lose the different answers. On the contrast, right, if you just go for pure learning, you might get a good spread over the different possible answers, but do less well on the side of physical accuracy. And right, there seems to be, to some extent, an inherent conflict between the two. Just to pick some of the methods. So this red dot here for CocoGen, this is one previously published method that does this inference time update. So that's why it's red here, that shows the time. This is actually fairly slow because it needs to run the physics residuals when producing a sample. And one variant that we tried, just to highlight the differences here, is this PBFM variant. This actually uses the same constraint at training time. So later on it's fast, but nonetheless manages to kind of push this kind of Pareto front between this accuracy and physics trade-off towards the lower left diagonal. Right, this was a variant here for this PBFM. And in a way, the main conclusion, I don't want to go into all the details here of how this can be combined, but it is actually through a gradient of the physics similar to the training as before. And this should indicate that it is also interesting in the context of generative models. We did look at a more real-world case. The previous one was a kind of a porous media scenario, looking at a dynamic stall case with tougher data for turbine blades, basically, with really potentially highly oscillating and varying behavior. We also found that this works potentially even better. So I don't want to go through all of the numbers here, but just looking at the main comparison between basically using the physics in the first area here, and in the second column, training a plain neural network without this physics constraint, you can see that especially in terms of the physics residual, that's the first number here, there's a substantial difference. And you actually don't lose much in terms of the other distributional metrics. Here the second was the Wasserstein distance for the whole distribution. In this case, it's actually even also slightly better. So, right, basically the takeaway also for this other case is that this is a useful combination. It does depend from our experience on what kind of constraints you can add. If it's too simplistic, like divergence freeness, it might not fully pay off. But in this case, for the rotor blades, it actually did provide a very nice kind of solidification of the answers of the diffusion model. Yeah, and with that, now I want to come to the conclusions of my talk. I've been talking about these differentiable solvers, and the main idea of the differentiability is to have solvers ideally, or the hope is that later on via autodiff, I think it's really promising to have solvers that just combine different of these differentiable and learned components in some manner that makes most sense for the different applications. There's a lot of flexibility here thanks to autodiff, and these AI components are really also, I think, a very promising outlook for accelerating parts of solvers. And I mentioned before, who knows whether foundation models will pay off more or these, but I think for solver development or many numerics and hence also for many applications, this will definitely have a lot of impact that's starting to show at the moment. Right, this differentiability provides integration and also very interesting applications like potentially inverse problems or generative modeling. And I think there's a lot of work to be done, right? So there's actually, for example, on the theory side, I think we're far away from really having a full grasp of what's happening here. So many open questions, many questions also with respect to architectures, and of course a combination of both, right? Using large-scale models or pre-training large-scale models, combining them with these differentiable solvers will be really interesting in the future. So I think there's plenty of interesting work left to do here. And I do want to close with one example from computer graphics works in my lab, which does not use any AI, but that's a nice reminder. It was classic numerics. You can actually get a lot out of the solver. So this is a really two-phase flow of a very, very turbulent ejection scenario, and the kind of detail and complexity of the structures that form here are just visually apparent without any further quantification here. So scaling up the networks and all these scenarios to these really large-scale phenomena, I think, is a very interesting challenge as an outlook. So with that, I want to thank the students that worked on this, shown here at the bottom, Björn, Giacomo, Chang, Liwei, and Benjamin especially. And if you're interested in details, we have a website that summarizes many of these topics with code examples. Thanks for listening. I'd be happy to answer questions. The question is about generalization of the networks for geometries. So our experience is that when training, the important thing is that whatever you want to vary later on at inference time, once you've trained your network, it's important to vary it beforehand. So if you train a network on one geometry, I would guess chances are very good or almost impossible that this will work on another geometry, because that's exactly what the training does, right? It's good at extracting the structures that reappear. So one geometry, it will completely overfit to that single geometry. But if you have multiple cases in multiple geometries, then I think chances are good that on similar ones, you will also get a reasonable answer. So that's usually the consideration here, that wherever you want to generalize later on, it's important to incorporate this into training of the networks. Very good. Yes, so for this scenario here specifically, Yes, the combination of these hybrid solvers, if we have a prediction by a solver and a network, then one of the potential impacts of this is if the network can learn structures that reappear independent of the geometry, then chances are good that it will work still without having seen that. So in general, the combination, if it's trained properly, can, I would argue, actually generalize better. That's one of the payoffs. That's a very good point. Yeah. We tried different geometries in other contexts. So you can definitely vary geometries. You can learn varying geometries, but the direct comparison of quantifying whether one or the other works better is a bit difficult because the direct predictions just work much less well anyway. So essentially for the errors will be huge if you don't have the solver in the loop. So it's a bit, they are less good overall. We have not tried to basically measure you could potentially measure the relative drop in accuracy from a baseline around this, but no, unfortunately I don't have numbers for that. Yeah.
Actually, you mentioned geometry. I was wondering, listening to you, where are the boundary conditions in all this?
Yes.
So normally in fluid mechanics, the accuracy on the numerical approximation on the solution might depend very much on the boundary conditions, how careful you are on catching the boundary conditions accurately using an appropriate solver.
Right. The boundary conditions do come into play typically both for the network and for the solver. Right? So the approximate solver would get the right boundary conditions ideally, and work with the right ones, and then the network. In the simplest case, it gets a state, for example, with an inflow condition or so, and in that way can use the boundary conditions. Or in other cases, you can actually also provide kind of global parameters directly as a conditioning or injected into the network. So if your solution depends on, let's say, a viscosity parameter or so, then it's usually good to make sure that the network has access to this parameter everywhere. So those need to be around here.
For instance, when you deal with incompressible Navier-Stokes, so you have normally the solvers take into consideration the incompressibility condition, divergence zero. Is this also built in the network somehow?
The divergence freeness constraints are typically not built into the networks directly. They're built into the solution, so the training data the network gets will be divergence free. But we didn't find it too useful to add additional constraints to the network. So in this back and forth between the solver, in this case, and the network, the normal Navier-Stokes solver, even the coarse one, typically guarantees divergence freeness on this coarse level in every step. So we typically don't need to make the network separately, explicitly divergence free. This comes into the picture through the solver. So, but this is potentially one of the also nice side effect that if you have hard constraints like divergence freeness, we should never leave the manifold of divergence free flow fields, then this is guaranteed by the solver part, and the network can learn to work with that.
So in the network you forget about the pressure, and you only deal with the velocity field?
In the cases I've shown, yes. They basically really just directly modify the velocities. Yeah.
Thanks for the nice talk again. I have a question regarding the differentiable solvers again in this hybrid setup. So can you maybe specify more what properties this solver gotta have? So is it always like a forced version of the true solution? Or is it just, I mean, I could also just train a new network which predicts not too accurate, which then get corrected by another network. Would this also work? Is it possible, or is it important to have this forced solver as the first one?
So the question was whether it makes or would be possible to use another network as a coarse solver, right? It's a good point. I mean, networks by definition are differentiable, right? Differentiability would be trivial. Potentially, in general, if you basically have a pre-trained network somewhere that gives you a first step to build on, then this might be a good idea to integrate in the same way. We haven't tried this, to be honest, explicitly. Typically, if you reduce the dimension of your solver, they are very fast. But if you don't have access to the solver and you pre-train something, this potentially works in a similar way. You definitely would have similar problems of this data shift, right? That you would need to train with the solver and combine it to look at the combined time evolution. Yeah, but no, this would be a very interesting avenue to try, to basically, instead of using a kind of classic numerical solver for the base part, to use a pre-trained one. And the generalization, potentially then the question of generalization becomes one of how well the base one generalizes, right? You have this interplay here. If you have a classic one, chances are good that it generalizes to some other scenarios and other parameter ranges. But that would be a question of validation for another setup. Then you measure the difference to a finely resolved one. Exactly. So for example, take a very low resolution finite element code, make a first step, and then you want this solution to match a very finely resolved one. Find time step, find spatial resolution, sample back onto the coarse grid, like coarse grading. That would be the simplest scenario, exactly. For training, you need, exactly. So you train with the fine ones, and the network learns the gap between coarse, low fidelity approximation and the fine ones. And in the other case, in the prediction case, right, there's no lower solve. You go from 0 to that target. In terms of the state, so imagine you have, right, for fluid flow, you have a state, velocity, xy velocity. And
what do you mean by state? So if I have finite volume, finite elements, or finite volumes, I store my state as a coefficient vector or as a vector of values for finite volumes. So mathematically, the state is a function in some discrete function space. What do you mean by state?
Right, but in the end, you want to map it to a velocity, right? You're interested in this, in your coefficients representing the velocity. Right, so you can imagine you have velocity samples here.
I cannot store any continuous vector field. So what do you store?
No, it's a discrete version, exactly, discretized velocity. Imagine you have discrete samples of...
So what is the
The
discretization?
discretization, right, whatever your solver does. If you have finite elements, right, you have your samples from your finite element solver. So whatever your solver produces, it's really, you can take any solver. Okay, so you can start with any finite element solver of your choice, produce the low-res state for your velocities, right? So right, we don't need the internal coefficients or anything, the final state of your physical system, the final outcome of your solver, velocity samples. Coarse as a starting point, and then you can take the same PDE, resolve it finely in space and time, and then you get a different answer, right? Typically it's nonlinear and you have different discretization errors, and that is the difference we're learning. Low fidelity and high fidelity solve for, right? But it could literally be any solver you choose, any discretized solver, right? And then on any discrete state you have, you can run a network. It's just a vector.
Okay, it's a vector. So
Yes.
you use some state that you store some finite vector. So you
A finite dimensional vector, yes.
that maps one state vector, one finite state, discrete state vector to another
Yes, no, that's why I had on the slide, it's no pins here. That from our experience actually does not work exactly. It's on the discrete level, you have a vector of unknowns from some solve. I mean, from this neural operator viewpoint, you can see it in terms of function approximations, but in the end, from our experience also, most of these actually truncate or have some discrete version in terms of some, whether it's internal neural network basis functions or some FFT basis functions. But I would recommend or we typically look at this as a discrete, relatively low-dimensional vector of the solution. Yeah. No, you don't need any high resolution, you just need a learning target, right? It can be statistics, it could be an experiment. You want your low resolution solve to match some other target.
And how can you mathematically deduce the high resolution solution from the low resolution one? So if I think of a PDE, I just define finite elements, very coarse and very fine, and the coarse discretization doesn't see certain features, so it will be
Exactly.
get from the coarse to the fine one.
Exactly, for numerical methods, exactly. That is what the network learns, exactly. That's exactly the whole point, right? Your low resolution solver has no chance to find, based on the coarse information, this missing information. It's under-resolved. The features are not there. But the network has seen a lot of training data or a lot of target statistics to know what they should match. And that's what the network can learn and bring into the solution. That's exactly the part that the network does in the correction setting. I mean, but from examples that seen before, exactly. I mean, it will do the same for the prediction task, right? Prediction has nothing and just needs to reproduce the data or interpolate it. And for the correction task, the only difference is that you make a step with the existing solver, so it has an easier job. It gets part of the solution. But it depends on how you set up the loss. So what we, for example, did for the 3D turbulence was primarily restrict the turbulence statistics for the first few moments, and those actually matched quite well. So I think this does look quite promising. The ones that were not in the loss were not necessarily matched closely, but also not too bad. So yeah. But this depends on the loss. There are caveats, and if you set this up, if it's under constrained on the loss part, it potentially could learn unphysical solutions. That definitely could happen.
I think, Martin, sorry, Martin, you wanted to ask something, no? It was the same hand. So I saw one hand. I didn't know which. Okay, so it was one shared hand. Okay, good. Albert.
Yeah, can you have non-differentiable components in your solver?
Non-differentiable components. Yes, very good question. So in this chain, we also did look at this in one paper because it's a very good question and a good thought. It does still help. You can, if you think about it, it basically doesn't necessarily, if you do this unrolling, expose the full attractor of your learned system, but nonetheless it helps to just vary the data that's seen at training time. It's a bit along the picture here with the warm-up steps. Right? So basically, if you have a non-differential solver, you can nonetheless compute these steps without backpropagating through the solver. You can still compute something local on this level, and basically at training time, the network will see different states or varied behavior. So it also helps. It's better than not doing any unrolling at all, but it's not good as really backpropagating through the chain. So it's a bit of a compromise in between, but it's still better than not exposing any of the time evolution. exactly.
And your corrector fixes it, so your simulation is stable.
Yeah.
How do you ensure this? Is there you cross your fingers and you hope that it works, or is there a way to guarantee that your simulation will be stable through the corrector?
No, there's no guarantee. Definitely not. No. I would argue actually for non-trivial real-world cases, also numerical solver is not guaranteed to be stable, right? You need to choose the right hyperparameters. You need to validate, and in a similar way, you need to validate the neural network. So I would actually argue it's not too simple, too different from classical numerical solvers, where you need to choose the hyperparameters, stabilization, hyperdiffusion, and other terms in a way that make it stable for your application. But there's definitely no guarantee. The network basically, as mentioned before, it just learns to approximate the target statistics or states, whatever you give it, in terms of all errors aggregated. So we try to fix both the difference in terms of states and potential blow-ups and satisfy those based on the capacity, on its size typically, right? The size is a key parameter. If the network is large, it can potentially learn a lot. Very small networks tend to kind of have this more under-constrained classic ML setting. Those are less stable. So the size of the network, in a way, again, the computational resources you invest into the neural network part play quite a role. And with this unrolling, we've had very good behavior. So the model stays stable, and you can train for the stability, but there's no a priori guarantee. Yeah. That would be an interesting question to study.
By introducing the solver, have you observed that the loss function becomes less smooth? Like you have to decrease the
Right. The smoothness of the loss function, that's a very good question. So I don't think we've really gathered statistics on smoothness for the combined loss function. Also here, the networks, we have relatively small ones, but still they have a few 100,000 parameters. So it's a pretty large gradient. So potentially, I think the solver actually does make them slightly steeper at least. What does play a role here is, yeah, I did not mention this before, but for these time chains, the evolution over time is really important. So here, with this example I've mentioned, it's up to 100 steps of the time evolution that you train with. And if your gradients or potentially the signals you get over the whole chain are not smooth, then any slight deviation, say, as introduced by the network over the 100 steps would explode and then also potentially turn your training into garbage. So what we typically do is that you start training with few steps to make sure the network stays in a reasonable range and the solver can work with the network, and then you increase that this unrolling chain. So this turns out to be a pretty important component for training this in a stable way, because otherwise the gradients would potentially destroy the state of your network early on in the training process.
No one has proven that theoretically.
Yes, no. I think theory also there would be an interesting avenue of work to have some guarantees on how the smoothness of the updates over these processes evolves.
One question more pending to the stability question.
Mm-hmm.
So in most papers I see regarding using these neural networks, you have somewhat small domains or resolutions compared to like enormous scale calculations like you showed in the last picture. So with numerical solvers, usually when you increase the resolution, the quality just gets better. So does the same apply also for this neural network model? So when I have a model running on 4 GPUs, 10 GPUs, also a simulation which is very big, does it have the same advantages as with medium or low resolution?
That's a good question. Scaling of neural network training, basically. I think this has been one of the weaknesses, I would say, in the past quite a bit. It's because it does not scale linearly, or usually it actually scales pretty badly. So increasing the network size has diminishing payoff. Potentially the hyperparameters change, right? It's a nonlinear learning process. So just making your network twice as large, your learning rate parameters might not work anymore. Or usually you will not see a twice as good model. So usually the order of convergence in terms of the errors is relatively bad for the networks. I think this is where the other component, these large-scale models, come in. This is something that could potentially be at least mitigated by pre-training large models. So I think these transformer models especially train really well. So these can now actually, what powers ChatGPT and co, they do scale to billions of parameters. It was not possible before with other architectures. And through that, I think there's hope of actually pre-training something. If you have a stable basis, similar here to the unrolling chains that you can build on, then it's easier to also make this work. So I think this goes a bit hand in hand with the current developments. There is, I think there's potential avenues, but it's not easy. I think the scalability of the networks is also an open issue. It's not easy to pull off. Yeah.
Any other question or comment? No?
Late enough.
18, 15.
Thanks for staying. Yes.
So maybe it's a good time to actually, well, maybe if I may. So in the last part you were talking about diffusion models and then how big you can go in dimension for these dimensional models, because when you are dealing with PDEs or numerical PDEs, then space-time, the dimension will be huge, right?
Right. So I've omitted this part, but I think with these transformer architectures also in our group by now, we have models that scale up to hundreds of millions of degrees of freedom, also for the diffusion systems. So they scale relatively nicely. It's still expensive to train. You need pretty big GPUs and a lot of training data, but it is, with the current architectures, it's possible.
So then eventually one can expect that out of these generative models, one will build new solutions of PDEs without actually solving the PDE again. That's the idea?
Yes. Well, so again, it's not magic, right? The model will not invent these from scratch, but if it has basically seen enough at training time, right? If you vary the geometry, maybe, then I think there's potential for generative models to really predict from scratch solutions for a new geometry or so. Yeah.
And there will be hallucinations, and then plenty of things to analyze.
Yes. No, definitely. The work is not done. Lots of work to do. Definitely.
Okay, so we thank Nils again. Thank you.
Thanks for the invite.